others, you may join the book club.
Good morning once again for this second day of Gyan program. Now we have, I think in this today's schedule, we have
Magnetism.
So day 2 we have lectures on magnetism. There are 2 lectures of 1.5 hours duration each by Process and Prem. And post lunch I will also be taking one lecture class of about 2 hours, somewhere around 2 hours of, I mean it would be on crystal structure determination through X-ray diffraction and TEM. I'll just give you all insight on how to index XRD data. Sir has asked me to talk about that, so I will be doing it post lunch. And maybe we can have a quick or small tutorial class if sir agrees.
Yeah.
Otherwise,
let me try to finish magnetism.
Okay,
If I
so-
cannot finish, then I'll cover the
okay,
remaining.
maybe then
Yeah.
tomorrow we'll have that tutorial. sir. So with this, I request Professor S.N. Prem to start with his lecture.
Okay. Thank you, Professor Naresh. Okay. Good morning, everyone. So please join the book lab if you haven't joined already. So today we'll learn the basic concepts of magnetism, which are relevant for magnetic recording. So quite often you all learn magnetism to some extent, but many of the applied aspects people don't describe very well during the magnetism classes. So this class I will try to cover magnetism in a way that's applicable to magnetic recording. Okay. So first question is this one. How did you come across magnets at first? Have you all joined? Looks like no one has joined. Okay. Okay, so school experiment with iron, lodestone, speaker, toy magnet, all these are some ways we have come across magnets, right? So what makes you feel fascinated about magnets is that their attraction or repulsion of magnets or magnetic materials. Okay? So this attraction or repulsion of magnets comes from the magnetic field produced by a magnet. Okay? So the magnetic field, I mean any magnets, any permanent magnet will exhibit a magnetic field. So this magnetic field shows many interesting properties, or we can use these properties for something. Okay. So for example, magnets attract magnetic materials. So this is the concept that we use for fridge magnets. So we stick things to the fridge because of this property, and we know that like poles repel each other, and this property we can use for motor, for example. And you would have learned Faraday's law, where if you have a time varying magnetic flux, you can generate electricity. So this is the one that we use for dynamo or power generators, transformers, and so on. And you can magnetize magnets with the north pole in one direction or south pole in another direction, and you can use this property for magnetic recording, and you can sense the magnetic field. So whether north pole is up or south pole is up, you can call them 1 or 0. So this property is also used in magnetic recording. And you also know that we can use the Earth's magnetic field for navigation. Okay, so there are many common uses of magnetism, and all these are connected to the magnetic field exhibited by magnets. Okay, so this brings us to the first question. Okay, majority of you have chosen Europeans. Okay, if you ask ChatGPT, right, ChatGPT will give you one answer. Okay, so I mean this is actually more correct than Europeans. Okay, but I asked who, right? I mean, I didn't mean limited to humans. Okay, even if you include microorganisms, birds, and so on, bacteria were the first organisms that used magnetic field for navigation. Okay, then migratory birds, sea turtles, insects, they all used magnetic field for navigation. Okay, so we are not the first. Humans are not the first to use magnetic field for navigation. So all these living organisms, bacteria are much older than humans, right? So they use magnetic field for navigation. So we are not the first. Okay, so you can use the magnetic, you can produce magnetic field by many different approaches. So one simple approach is by sending a current through a wire. You can use, you can make solenoids and can generate a magnetic field, and you can also use electromagnets or permanent magnets to generate magnetic field. Okay. So let's go through one by one. So if you send a current through a current carrying wire, you can produce a magnetic field, and the magnetic field direction is in the direction of my fingers. For example, if the current is flowing in the direction of my thumb, then the magnetic field will be in the direction of my fingers. Okay. So that is the concept discovered by Oersted. So yesterday Professor Animesh told you that Oersted discovered this, but Oersted didn't describe why magnetic field is produced. Okay, so when you send a current, you can produce a magnetic field, but why is the magnetic field produced? Oersted didn't describe, because this is a relativistic phenomenon. I don't know how many of you watch YouTube channels. So if you know Veritasium, so Veritasium has a video explaining why moving charges produce magnetic field. Okay, so it's based on relativistic concept of your space dilation, length dilation, and that is the reason why we can produce a magnetic field by sending current through a wire. So Oersted didn't say the reason, because at his time there was no relativity. Okay, Oersted was like in 1800s. Relativity came in 1900. Okay, so we can produce a magnetic field due to a current carrying wire. So this is one approach. Another approach is you can wind a wire in the form of a coil or solenoid, and here again you can send a current through the wire and you can produce a magnetic field. So in this case, the number of turns that you have per given length, that determines the magnetic field strength. So in the first case, it's only the current. So as you go away from the current carrying wire, the magnetic field will reduce. In the case of solenoid, if you wind more coil in a given length, then you can produce a stronger magnetic field. So in your school days, probably you would have used a Helmholtz coil. So that's a kind of solenoid where you can produce magnetic field. Okay, but even solenoid cannot produce very strong magnetic field unless it is a superconducting solenoid. Otherwise, if you want to produce strong magnetic field, we use electromagnets with a core. Okay, so in this case, what you have is, for example, this region and this region, you have a solenoid. Okay, so you have coil wound around this region, and in between there is a hole, and inside the hole you introduce a ferromagnetic material with a large permeability. Permeability is a property that describes how much magnetic field can go through the magnetic material. Okay, so for time being, you can imagine that this is a number greater than 1. Okay, so magnetic materials have a permeability much larger than 1. So if you take iron, for example, it may have a permeability of around 100. So you see, now the magnetic field produced by the same coil is multiplied by this factor mu r. Okay. So, you can produce much stronger magnetic field than a solenoid without a core. Core basically represents a ferromagnetic material with a high permeability mu r. Okay. So, when you introduce this core, here you can see that there is a gray color metallic thing. So, that is a magnetic material with a high permeability. So, once you insert that, you will be able to amplify the magnetic field. So, that is the concept of electromagnetics with a ferromagnetic core. Okay. For example, if you send a current through a solenoid, let us say current is 1 ampere and you have 100 turns per meter, then the field strength you produce will be like only 100 ampere per meter, which is 0.0013 Tesla. So, these are units that we use for measuring magnetic field. I think yesterday you learnt about the units. So, quite often I might use SI unit, but sometime I will also use CGS unit. So, please bear with me. Now, here I am using SI unit. Okay, so, if you want to produce 1.3 Tesla, which is commonly available in many labs, just using solenoid you need to send 1000 ampere, okay, which is too large a current. On the other hand, if you insert a ferromagnetic material of permeability 100 inside the solenoid, then you will be able to amplify this field. Okay. So, you will get 1.3 Tesla with a current of just 10 ampere. Okay. So, you can see what the ferromagnet that you insert here does, right. So, it amplifies the magnetic field by a factor which is related to the permeability of the magnetic material. Okay. So, let us do some questions. Okay, when you send a current through a wire, if the wire has some resistance, so there will be Joule heating. So, this is correct. The wire will produce a magnetic field, this is correct. And when the wire has a resistance, there will be a potential difference between the ends. So, all of the above is the correct answer, and most of you are right. Okay, next question. Okay, most of you are right. The magnetic field of a solenoid depends on the number of turns in the coil. So, this is correct. It depends on the current. So, independent of the current is not correct answer. Next one. So, if you have not joined, just go to wooklab.com and use this code to join. Okay, so, you cannot enhance the magnetic field of a solenoid more efficiently by increasing the turns. Okay. So, the efficient way is to insert a ferromagnetic material. So, just inserting a ferromagnetic material with a permeability of 100 can enhance the magnetic field by 100 times. Okay. So, the correct answer is number 3. Okay, so, you can also produce a magnetic field by having a permanent magnet. Okay. So, typical neodymium iron boron magnets generate around 0.1 Tesla near the poles of the magnet. So, you can generate some moderate magnetic field using permanent magnets. Okay. So, if you look at the magnetic field that comes from a solenoid or bar magnet, they will look almost similar. Okay. So, solenoid will have a north pole, south pole, and magnetic flux goes from north pole to the south pole. So, this is the convention. By convention, we say that the magnetic fields come out of the north pole and enter into the south pole. So, similar behavior you will also see in bar magnet. Okay. But in solenoid, we send a current through the coils to produce a magnetic field. But in the case of a bar magnet, we do not send any current. Okay. We can still produce a magnetic field. So, what makes a bar magnet to generate a magnetic field and why bar magnets are special is what we are going to learn in the next few minutes. Okay. So, in the case of solenoid, we send current, we produce magnetic field. So, that is classical electrodynamics. So, when we talk about a permanent magnet, why it produces magnetic field, then we need to discuss quantum mechanics. But I will not go through the details of quantum mechanics, but I will touch upon a few basic aspects. Okay. So, quantum mechanically, we know that there are orbital magnetic moment and spin magnetic moment associated with electrons, and these are the properties that give rise to the magnetic properties that we see in materials. Okay. So, we will go through this in detail. So, for all the future discussion from now onwards, I will use the word magnetic moment. Okay. So, magnetic moment basically represents a tiny magnetic dipole. Okay. So, you know that magnets have two poles. Okay. Magnets have two poles and we call them dipole, magnetic dipole. Okay. So, when I talk about magnetic moment, I am going to talk about very tiny magnetic dipole. Okay. So, we may not use this symbol, we use arrow to represent magnetic moment. Okay. So, moving forward, most of the time when I draw an arrow, it represents magnetic moment or some other property which we will learn later, magnetization and so on. Okay. So, later I will explain what is magnetization. So, time being, just remember that a magnetic moment is very similar to having a magnet with two poles. Okay. So, these two are analogous, but only thing is this one is very tiny and of a very less magnitude. Okay. So, remember this one. Okay, so before that, let me ask you a question. Okay, so most of you have chosen iron. Now, imagine that you are a middle school student. Okay, let's say imagine that you haven't studied undergrad or master degree. Imagine as a middle school student and answer why you chose iron. Okay. Okay, magnet attracts iron. Iron got attracted by magnet. Okay, so this is the type of answers I expect as a middle school student. This is what you learn, right? So, if some material get attracted by magnet, then we call them as a magnetic material. And here in this case, we chose iron because it gets attracted by a magnet. Okay, so this is how a common person classifies material, whether they are magnetic or non-magnetic. Okay, so if someone hasn't studied physics in detail, then they will classify magnetic materials as the one that get attracted, and if some materials do not get attracted to magnet, they call it non-magnetic material. So, this is a layperson classification, but in physics we classify magnetic materials and non-magnetic materials into various class of magnetic materials. So, in physics all are some sort of magnetic materials and they respond to magnetic field in certain different ways, and we have name for all of them. Okay. So, here I have listed 5 names. There is also a new name which came 2-3 years ago, which is called alter magnetism. Okay. So, but let us not go into that complication. So, we will focus on these 5 aspects of magnetic materials. So, ferromagnetic and ferrimagnetic materials are the one that get attracted to magnets, and paramagnetic, diamagnetic and antiferromagnetic materials, they also respond to a magnet, okay, but in a very weak sense. Paramagnetic materials will be weakly attracted to ferromagnet magnet. Diamagnet materials will be weakly repelled by magnets, and antiferromagnetic materials are similar to this material in some sense, but they don't exhibit attractive properties. So we'll go through a few details of all these materials first. Okay, so a layperson classifies materials into two categories just based on whether they get attracted or not. Okay, so some examples of ferromagnetic materials are iron, cobalt, etc. And ferrimagnetic materials are like ferrite. So, for example, if you look at the fridge magnet, it's black in color, that's basically some sort of ferrite. So, those are ferrimagnetic materials. Aluminium, ruthenium are paramagnetic materials, copper is diamagnetic, and the antiferromagnetic materials are like manganese, chromium, and some compound alloys like this. So, as I mentioned, you can just check whether a material is ferro or ferri just by seeing whether it gets attracted or not. The effect is very clearly visible, but paramagnetic materials, their attraction is very weak, and diamagnetic material, their repulsion also is very weak. So, if you want to measure or find out whether a material is ferromagnetic or paramagnetic or diamagnetic, we need to use some sort of magnetometers to observe the different properties. Okay. So, I told you that diamagnetic materials get repelled by magnet, right. So, if you take a frog, for example, the body weight of a frog is mostly like 80% by water. Okay. Water is a diamagnetic material. Okay. So, in this experiment, what these researchers did was they placed a frog on top of a strong magnet, 8 Tesla magnet. So, they placed a frog, okay, frog being light and it has water, and water being diamagnetic, the magnet repelled the frog, and you can see the frog is floating. So, this is some kind of magnetic levitation. Okay, so, you levitate a frog using magnetic field, and because of the diamagnetic property. Okay, so, this is another video to demonstrate the repulsion between magnet and the diamagnetic material. Okay, so, in this case you see that this guy has a strong magnet, and he is going to push this water away. Okay. So, there is a beaker with water, and you can see that the water is getting repelled by the magnet. Okay. So, the floating water and the floating this piece on water helps to reduce the friction. So, you can see the repulsion between water and the magnet easily. Okay. So, those are some experiments that show that there is a repulsion between magnet and diamagnetic material. Okay, so, moving forward, we will learn how the magnetic properties arise. Okay. So, for that, remember that we have the concept of magnetic fields, magnetic dipoles. So, in electrostatics, you learn about electric dipoles. That means, you place two charges close to each other, then you will produce electric field like this. So, this is what we call as electric dipole. So, in a similar sense, we also have magnetic dipoles. So, where we keep north pole and south pole of a magnet next to each other, and they produce magnetic field. Okay. Although charges can exist in isolation, magnetic poles do not exist in isolation. Okay. Magnetic poles are always together. You take any magnet, there will be a north and south pole. If you cut this into two pieces, again the two pieces will have a north and south pole each. Okay, so, as I mentioned briefly that this magnetic property is coming from the magnetic moments of electrons. Okay. So, you know that in atoms you have a nucleus, and the electrons are going around the nucleus, and that produces orbital magnetic moment. So, you know, whenever a charge is in motion, there is a magnetic field. So, that is what we learned a few minutes ago, right. So, in a similar sense, when an electron goes around the nucleus, it produces a tiny magnetic field, and this is what we call as orbital magnetic moment. Okay. So, in addition, the electrons also have a spin magnetic moment, which you would have learnt in quantum mechanics. So, time being, let us start with the assumption that any of these two may be able to contribute to the magnetic properties of the material. So, you can actually calculate, we express the orbital magnetic moment of electron in a elementary unit called Bohr magneton. So, Bohr magneton has this value of 9.27 times 10 power minus 24 ampere meter square. So, but basically that is equivalent to sending a current of 10 microampere through a wire which has 1 nanometer dimension. Okay. So, you have a square loop and you send a current of 10 microampere, then you will produce one Bohr magneton. So, it is such a tiny value, and this is the elementary magnet. Okay. So, for the next few minutes, we will be talking about Bohr magneton. So, imagine that Bohr magneton represents the magnetic property of a tiny magnetic dipole. So, which we will call magnetic moment. Okay, so, orbital magnetic moment is one thing. Then the second aspect you would have learnt in quantum mechanics is spin. So, you would have learnt that electrons have spin. So, you can define electron spin in many different ways. So, I mean the accurate method is that electron spin is an angular momentum intrinsic to electron, and this has a quantum mechanical origin, and this comes from the 1900s when people try to understand the spectroscopy. They try to explain the spectroscopy results, and they need something else to explain the spectroscopy results, and they realize that electrons have a property called spin. Okay. So, if this is difficult to imagine, you can visualize that spin is like an electron rotating about its own axis, some charge of electron that is rotating about its own axis, then it will produce a tiny magnet. So, you can imagine that as a spin, but this is not an accurate answer, this is an incorrect picture. But if you like analogies, you can imagine that way. And another way of explaining spin is like charges are responsible for electricity, right. So, when you talk about conductivity in a wire, we say that electrons move, and in semiconductor we say holes move. Okay. So, the electrical transport happens because of motion of charges. So, similarly, you can say that spin is responsible for magnetism. And the fourth answer is accept spin as spin. Okay. So, in your electricity course, your teacher would have said electrons have charges, okay, and you accepted charge as it is. You did not ask what is charge, whether it is 1 rupee or 10 rupees, you did not ask, right. You just accepted charge as it is. So, similarly, accept spin as spin. Okay. So, these are 4 different answers that I can give about spin, but in brief, spin is the major contributor for many phenomena that we will observe in magnetism. So, now let us move on to the detail. So, you all know that iron is one of the well known magnetic material. Okay. So, before we move on, I should say that even though we talked about orbital magnetic moment, in most of the materials like iron, cobalt, nickel that we commonly use as ferromagnetic material, the contribution of orbital moment is almost 0. Okay. So, it is negligible. So, people use the word quenched. So, in quantum mechanics we use this term quenched. Basically, that means the orbital magnetic moment contribution is 0, negligible. Okay. So, we do not consider this further. So, most of the contribution to the magnetism is coming from the spin of the electrons. Okay. Electrons move, and in semiconductor we say holes move. Okay. So, the electrical transport happens because of motion of charges. So, similarly, we can say that spin is responsible for magnetism, and the fourth answer is accept spin as spin. Okay. So, in your electricity course, your teacher would have said electrons have charges, okay, and you accepted charge as it is. You did not ask what is charge, whether it is 1 rupee or 10 rupees, you did not ask, right? You just accepted charge as it is. So, similarly, accept spin as spin. Okay. So, these are 4 different answers that I can give about spin, but in brief, spin is the major contributor for many phenomena that we will observe in magnetism. So, now let us move on to the detail. So, you all know that iron is one of the well known magnetic material. Okay. So, before we move on, I should say that even though we talked about orbital magnetic moment, in most of the materials like iron, cobalt, nickel that we commonly use as ferromagnetic material, the contribution of orbital moment is almost 0. Okay. So, it is negligible. So, people use the word quenched. So, in quantum mechanics we use this term quenched. Basically, that means the orbital magnetic moment contribution is 0, negligible. Okay. So, we do not consider this further. So, most of the contribution to the magnetism is coming from the spin of the electrons. Okay. So, now let us move on to understand what happens in an atom. Okay. So, now here I am taking an iron atom as an example. So, you know that iron has 26 electrons. So, this is the nucleus of iron, and let us say this represents the 1s, 2s, 2p and so on. So, we have so many shells surrounding the iron nucleus, and you know that we fill the atoms the orbitals in this order. So, we start with 1s, 2s, 2p, 3s, 3p, then we do not go to 3d, but we go to 4s, then 3d, 4p and so on. Okay. So, if you take the 26 electrons of iron and you start filling, first you will fill the 1s shell with 1 spin up and 1 spin down, then the 2s you will fill again with 1 spin up, 1 spin down, then 2p will have 6 electrons. So, there will be 3 up and 3 spin downs, and 3s will have 2 and 3p will have again 6. Okay. Now, after 3p you fill the 4s. Okay. So, 4s will have 1 up and 1 spin down. Okay. So, that is roughly 20 electrons. Okay. So, we are left with the 6 electrons. So, these 6 electrons, first 5 up spins will occupy the 3d, then we will be left with 1 down spin. Okay. So, imagine that these are tiny magnetic fields. So, in all the other shells 1s, 2s all the way to 4s, you can see that there is a compensated spin. So, you can imagine that the magnetic field produced by this spin will be cancelled by this spin. Okay. However, if you look at the 3D shells, there are 5 up spins and 1 down spin, okay, which means let us say if each electron spin as a value of 1 Bohr magneton. Okay. So, here we have 5 up spin and 1 down spin. So, we can say that iron atom will have a net magnetic moment of 4 Bohr magneton per atom. Okay. So, remember that each electron spin has a 1 Bohr magneton value, and all the other spins have compensated spins. That means, for every up spin there is one down spin, except for these 4 spins. Okay. So, we can say that this iron atom has 4 Bohr magneton per atom. Okay. So, this gives us some clue that what makes iron as a ferromagnetic material, which means there is a unpaired electron. Okay. So, if you look at the commonly known materials like iron, cobalt, nickel, which are ferromagnetic materials, you notice that they have some unpaired electrons. So, iron has 4 unpaired electrons, cobalt has 3 unpaired electrons, nickel has 2 unpaired electrons. So, this gives you some clue that we need unpaired electrons to get some magnetic property. But okay, we can also see roughly that iron has more unpaired electrons than cobalt, and cobalt has more unpaired electrons than nickel. So, there is also some other way we can interpret iron may have better magnetic properties than cobalt and so on. Okay. So, we can roughly infer something just by looking at the unpaired electrons in the atom. Okay. But it is not that simple. Now, if you look at chromium, chromium also has 5 unpaired electrons, manganese also has 5 unpaired electrons, and you know that chromium is non-magnetic and manganese also is not magnetic. Okay. So, something else matters. So, it is not that atomic magnetic moment. So, I just told you that iron atom has this 4 Bohr magneton. So, this is what we call atomic magnetic moment. So, it is not just that the atomic magnetic moment matters, but something else also matters. Okay. These are not ferromagnetic, but the other 3 are ferromagnetic. Right. So, long back, okay, I think we can skip this one. Okay, so, we had two problems, right. One case we have iron, cobalt, nickel, they have certain magnetic moment per atom and they are ferromagnetic, we know that. On the other hand, chromium, manganese, they also have certain value of Bohr magneton per atom, but they are not magnetic. Okay, so, this atomic magnetic moment is a necessary condition, we can say. But it is not a sufficient condition. Okay. So, having some atomic moment alone is not sufficient to make a material magnetic. Okay. So, there is something else that matters. Okay. So, let us say we have iron atom with a 4 Bohr magneton, and let us say we place a few of the atomic magnets together. Okay. So, there are a few possibilities. So, one possibility is that the neighboring atomic moments all point parallel to each other. Another possibility is that the neighboring magnetic moments are pointing anti-parallel to each other. Okay, so, this is a possibility 1. This is another possibility. Then another possibility is that there is no order, they can be in random. direction. Okay. So, there are many possibilities, and these possibilities determine whether a material becomes ferromagnetic or antiferromagnetic and so on. Okay. So, as I mentioned, there was some explanation before Weiss molecular theory to explain the ferromagnetic material, but that is obsolete and outdated. So, we will not go into that. So, Heisenberg was the first one to produce to explain the quantum mechanical origin of ferromagnetic and antiferromagnetic properties. Okay. So, Heisenberg came up with this formulation that energy of the two spins, for example, if S1 and S2 represent two spins. Okay, so, these are vectors. Okay, so, the energy of the two spins next to each other is given by this formula, where J is called the Heisenberg exchange integral. So, all these are coming from quantum mechanics. Okay, so, the energy is given by minus J S1 dot S2. So, this is a dot product between these two spins. Okay, so, now imagine if J is positive, then when S1 and S2 are parallel, then the energy will be the lowest. So, you all know that the energy of physical systems will be at the lowest, right. So, if J is positive, the lowest energy is obtained when S1 and S2 are parallel. Okay, if J is negative, then lowest energy is obtained when S1 and S2 are antiparallel, and if there is no J, then the material will have nothing to force. Okay. The thermal energy will make the spins in random direction. Okay. So, this is what gives rise to the ferromagnetic and antiferromagnetic properties. Okay. So, for example, in ferromagnetic materials, all the neighboring spins are aligned parallel to each other. So, if you take iron, cobalt, nickel, so in all these materials, the neighboring spins will be parallel to each other. That is because in these systems, the J is positive and the energy will be the lowest when the neighboring atoms spins are parallel to each other. Okay. So, in ferromagnetic materials, the neighboring spins are parallel to each other, and in antiferromagnetic materials, J is negative. So, the energy is lowest when the neighboring spins are antiparallel to each other. Okay. So, this class of materials are called antiferromagnetic materials. Okay. Then there is also a subset of antiferromagnetic materials, where the neighboring spins are antiparallel to each other, but the two spins S1 and S2 are not the same. Okay. So, the vectors are pointing in the opposite direction, but their magnitudes are different. Okay. So, this kind of materials give rise to the ferrimagnetic property. So, if you have learnt about ferrite, ferrites belong to ferrimagnetic property. So, in ferrite, the neighboring spins are antiparallel to each other, but they are of two different magnitudes. So, the S1 is not equal to S2. So, although I haven't taught you magnetization yet, but I will just say that in antiferromagnetic material, there is no magnetization, zero magnetization, because you can see that the neighboring spins are in antiparallel direction and they are equal in magnitude. But ferromagnetic materials and ferrimagnetic materials, you can see that the spins are not compensated. Okay. As a result, they have a net magnetization. So, this is how we can explain the ferromagnetic, ferrimagnetic and antiferromagnetic materials. Let me skip this one. And in the case of paramagnetic materials, there is no energy to hold the spins next to each other. So, you can imagine that the exchange integral, I mean there is no exchange energy to keep them parallel, and because of the temperature the spins are in random direction and they also fluctuate as a function of time. So, if you look at the spins at time t1 they may be like this, at time t2 all the spins would have flipped to some other direction. Okay. So, here again because of the randomness these materials have 0 magnetization. And another point that you should know is that all ferromagnetic materials are paramagnetic above Curie temperature. This also we will learn. Above certain temperature, the ferromagnetic materials will lose their ferromagnetic property and they will become paramagnetic. So, this is also another concept that you should know. Okay, so, this video basically summarizes the 3 class of materials. Okay, this is not paraferro, this is called paramagnetic material. Okay, so, in ferromagnetic materials the neighboring spins are parallel and you can say they are stable most of the time, and in antiferromagnetic material the neighboring spins are anti-parallel to each other, again they are stable as a function of time, whereas in paramagnetic material the neighboring spins are random and they fluctuate as a function of time. Okay. So, this is how you can understand the 3 different class of material. And in ferrimagnetic material the spin configuration is similar, but the magnitude of the 2 spins are different. Okay. Now, we go through some questions to reinforce these concepts. Okay, most of you are wrong. Okay, something is what is the meaning of this rotation of a magnet around a center? Some nonsense. Okay, so I put some nonsense as one of the answer. So, this cannot be an answer. So, if this is not an answer, this cannot be the answer. Okay. So, as I mentioned, magnetic moment means a tiny magnetic dipole, that is the answer. The answer is already in the board. Okay, so, whenever I say magnetic moment, I am talking about a tiny magnet. Okay. Magnet has 2 poles. So, it is a tiny magnetic dipole, that is what I mean by magnetic moment. Okay, next question. Okay, there are many wrong answers, but the correct answer is uncompensated spin moment of electrons. So, I told you that iron has 26 electrons, right. So, if magnetic moment come from the spin moment of electron, then there should be 26 Bohr magneton, but we do not have 26 Bohr magneton. We only have 4 Bohr magneton per iron atom, because there are only 4 spins which are not compensated. All the other spins have, if there is one spin up, there is one spin down. So, this is compensated, but if there is more up spin and less down spin, especially in the 3D, shell, you have 5 up spin and 1 down spin, okay, which means this is already compensated, this does not come into picture. So, you have only 4 uncompensated spins. So, these 4 uncompensated spins are the one that gives rise to this 4 Bohr magneton per atom. Okay. So, it is the uncompensated spin moment of the electron that give rise to the magnetic moment of iron atom. Okay. Next question. Okay, here all of you are right. So, in antiferromagnetic materials, the neighboring spins are antiparallel to each other. So, I use the word not magnetic. So, in physics, we call this property as antiferromagnetic. Okay. So, when the neighboring spins are antiparallel to each other, so we call this type of materials as antiferromagnetic. Okay. Next question. Okay, so, in ferrimagnetic material, there are at least 2 types of atoms with different magnetic moment values, that is correct, and the magnetic moments are aligned in antiparallel directions, that is also correct. So, you should have chosen both answers. Okay. Okay, so, in ferrimagnetic materials, what happens is you have, let us say, one up spin, there is a down spin with a slightly different magnitude. Okay. Okay, so, this type of materials are what we call ferrimagnetic. Okay, so, I will play a video and observe what is happening, and you should write what you observe. Okay. Now, we have a OCLAP question. please type in your observation. Magnets or okay, usually I don't expect a correct answer for this question. Okay, the reason why I show this video, now I tell you, then you observe again. So, when the magnets are isolated like this, right, so this magnet, for example, it will attract maybe one of these neighbors, and as it grows longer and longer, then you will notice that the long magnet attracts magnet even from farther away. Okay. So, now you watch the video again. Initially they attract from the neighbor, but once it becomes longer and longer, it can attract magnet from far away. Okay, so this is a very toy example to make you pay attention to the concept of magnetization. Okay. So, in atoms we have tiny, in material we have tiny atoms, each has magnetic moment. So, when the magnetic moments are all parallel, they add together. Okay. If they are anti-parallel, they are destructive, they do not add together. Okay. So, that belongs to, that brings us to a property called magnetization. Okay. For example, let us say you receive 1 rupee from one person, another 1 rupee from another person, another 1 rupee from another person. If you keep adding, you receive 1 rupee from say 1 billion people, then you will have 1 billion rupees, right. So, here all the money gets added together. On the other hand, let us say you receive 1 rupee from one person, you give back 1 rupee to another person, you receive 1, you give 1, and so on. Then in that case 1 minus 1 plus 1 minus 1, all this will lead to having 0, right, 0 rupees in your hand. So, in a similar sense, you can imagine one iron atom has 4 Bohr magneton. So, you put many iron atoms together. So, all these magnetic moments will get added together. Okay. On the other hand, in the antiferromagnetic material, let us say this atom has 4 Bohr magneton, but this one is like minus 4 Bohr magneton. Okay. So, they get cancelled. So, we have a property in physics called magnetization, which is the sum of the magnetic moments of all these tiny atomic magnetic moments. So, you add them together and divide by volume or mass of the material. Okay. Let us say you have 1 cubic meter of certain material, you take all the magnet atoms, add their Bohr magneton together, divide by the volume, you will get this property called magnetization. So, you can also divide by mass. Okay. So, in CGS unit, we use EMU to represent a property called magnetic moment. Okay. So, we can either divide by volume, EMU per cc, cubic centimeter, or EMU per gram. So, people express magnetization in EMU per cc. Cc represents cubic centimeter volume and gram represents weight. Okay, you can divide by the mass or volume to get magnetization. Okay. So, this property is called magnetization, and let us say you apply certain magnetic field and force all the magnetization in one particular direction, then you will have a property called saturation magnetization. Okay. So, these are terms that we will learn in more detail in the next few slides. Okay, for example, let us say 1 Bohr magneton is equal to 0.9274 times 10 power minus 20 EMU. So, 1 gram of iron will have so many atoms, right, and each atom has 4 Bohr magneton, and this will give rise to 1 gram of iron to have 400 EMU per gram. Okay. So, this is the number that you will get if you just calculate the magnetization of iron based on the concept that we discussed. So, I told you that iron has 4 Bohr magneton per atom, and if you go with that, then you will notice that the magnetization of iron is 400 EMU per gram, but this value is larger. Okay. If I give you a piece of iron and I ask you to calculate the magnetization of iron, then you go to the lab, do some measurement, then you will come back with the value of 220 EMU per gram, something like this. Okay. So, this is what we will get experimentally. Okay, experimentally, if I give you a piece of iron and you go and measure the magnetization of iron, you will come back with a value of 220 EMU per gram. Okay. If you come back with that value, I will accept. Okay. Suppose you learnt in my class that iron has 400 EMU per gram. You go and measure, then if you come back to me telling that my measured sample has 400 EMU per gram, I will reject. Okay. I will think that you have done some manipulation. Okay. But okay, so you see that there is a difference. Experimentally, it is 220 EMU per gram, but from whatever I taught you, it is 400 EMU per gram. So, why is it vastly different? It is because we are thinking of iron as an atom, and we are calculating the magnetization just taking the atomic magnetic moment. Okay. But when you have a piece of iron, right, so you have a piece of solid. So, in solid we have band structure. Okay. So, solids properties will be slightly different from the properties of the atoms alone. So, when you have a solid, you will have band structure, and if you look at the band structure, there will be density of states and so on. So, you will have certain density of states for up spin, certain density of states for down spins, and if you do the band structure calculation, then you will realize that the magnetic moment of iron is roughly 2.2 Bohr magneton per atom. Okay. If you take isolated iron atom, it will have 4 Bohr magneton per atom. Okay. Isolated iron atom. But in a solid, we have many atoms. So, there is a band structure and so on. So, in a solid, because of the band structures, now it will turn out to be 2.2 Bohr magneton per atom. Okay. So, because of this reason, when you go and measure the magnetic property of iron, you will come up with the value of 220 EMU per gram. You will not get 400 EMU per gram. So, I was using a very simple picture of atoms having their magnetic moment of certain value, putting them together, they have neighboring spins parallel to each other and so on. Okay, this is a very simple picture, but in reality the band structures are the one that determines the final magnetic moment. So, in the case of iron, it will be 2.2 Bohr magneton per atom. Okay. So, if you look at this table, you will notice that iron has roughly 2.218 Bohr magneton per atom, cobalt has like 1.71 Bohr magneton per atom, nickel has a Bohr 0.604 Bohr magneton per atom. So, you can also see that this is reflected in the MS values. So, the one with the highest Bohr magneton per atom has the highest MS 1714 EMU per cc, and this is in the middle. So, it has a medium value of magnetization 1422, and this has the lowest Bohr magneton per atom nickel, and you can see its magnetization is lower. Okay. Okay, so, as a summary, we can say that atoms have uncompensated spins. So, the uncompensated spins are the one that gives rise to the atomic property, and how they arranged, whether they are parallel or antiparallel, or whether they have no order, that determines the magnetic property. Okay. So, eventually the band structure is the one that determines the magnetic property. Okay. So, yesterday someone asked me whether you can make magnetic material without any of the elements, like we know that iron, cobalt, nickel are ferromagnetic material. Most of the magnetic materials that you see will be made using any of these. Okay. So, it may be an alloy of iron, cobalt, nickel or something like that, but we can also make ferro or ferrimagnetic materials without these three elements. Okay. For example, if you take chrome platinum 3, this is I think antiferromagnetic. Okay. Some of them are ferromagnetic here. So, we can make also ferro or ferrimagnetic materials without this. So, what ultimately matters is the electronic band structure. Okay. So, the concept of this density of states. So, how many of them are up, how many down, the density of states, that determines the final magnetic property. Okay. So, with that, let us move on to do some questions. Okay, so A, B, C have like 2.2, 1 and 1.7. So, in the order of increasing saturation magnetization, then it should be B, C and A. Okay, so, most of you are right. So, I told you that above certain temperature, ferromagnetic materials will become paramagnetic materials. So, this picture shows what happens. So, in the x axis you have temperature, okay. Then in the y axis you have some other property here. on this side you have M. So, let me use the pen. So, below the Curie temperature, the plot is about magnetization, and above the Curie temperature, it is plotting 1 over chi. Okay, we will discuss that later, what chi is. Okay. So, you can notice that when we increase the temperature, so we go from left to right, we are increasing the temperature, the magnetization of the material drops, and at some point it becomes 0. Somewhere here it reduces to 0, and above T we have some other property we will learn later. So, it becomes paramagnetic. Okay. So, this temperature is called Curie temperature. So, you can also see the difference, right. Below Curie temperature, the neighboring magnetic moments are aligned parallel to each other, but above Curie temperature the spins are random and they are fluctuating as a function of time. So, different materials have different Curie temperature. For example, if you take iron, it has a Curie temperature of around 780, and iron oxide has a Curie temperature of around 560, and so on. Okay. So, different materials have different Curie temperature, and above Curie temperature they will lose their magnetic properties. They will become paramagnetic. Okay. So, this video demonstrates the concept of Curie temperature. So, here we have a magnet, okay, then here we have a clip. The clip is tied with a string, and because of the force of attraction between the magnet and the clip is attracted. But once you heat the clip using a flame, the temperature rises, and the clip reaches its Curie point, and it becomes paramagnetic, and you lose the force of attraction between the magnet and the clip. So, the clip falls down. Okay. So, you notice that at room temperature the clip has ferromagnetic property, so it gets attracted, but once you heat, the clip becomes paramagnetic and the force is gone, the object falls down. Okay. So, this explains the concept of Curie temperature. Okay. So, now the clip is lying down, it got cooled to room temperature. So, will the clip become ferromagnetic again? Yes. Okay. So, if you look at this picture, so above this temperature it will become paramagnetic, but if you cool again it will become ferromagnetic. So, this curve is more or less reversible. Some materials may have some hysteresis loop here, but mostly it will go back along this path. Okay. So, materials will gain the ferromagnetic property again once you cool down below Curie temperature. Okay. So, this is a brief mind map of whatever we learned so far. So, in the start of this lecture, we learned that there are two possible contributions to magnetism. One is orbital moment and another is spin moment. So, I told you that the orbital moment of iron, cobalt, nickel are quenched, they have no contribution. So, we just skipped this part and focused on a spin moment. So, here again you have like two types of materials. Atoms with the filled shells. So, they belong to diamagnetic materials, which we will not discuss, and there are atoms with unfilled shells, okay, like iron, cobalt, nickel. There we have some net magnetic moment per atom because of the uncompensated spins, and if they are ordered, then we will have ferro, ferri or antiferromagnetic property, and if the net magnetic moments are not ordered, if they are random. So, if they are random like this, then we will get paramagnetic, and if they are ordered means here they are parallelly ordered, here they are antiparallelly ordered. So, all these are ordered materials. So, ordered spins belong to ferro, ferri or antiferromagnetic nature. Okay, so far we have learnt a few things, like we have learnt about paramagnetic materials, that means they have no order. So, materials like aluminum belong to paramagnetic nature, and water, copper, they all belong to diamagnetic category, and materials like iron, cobalt, nickel are ferromagnetic materials, and ferrites are ferrimagnetic materials, and materials like chromium, manganese, they belong to antiferromagnetic category. Okay, so, common people always call ferro or ferrimagnetic materials as a magnetic materials. Okay, with that I think we can have a break. So, we will have tea break, then come back to learn the other aspects.